entitled The Cavity Care Medium Model and the Surprising History Around It. Our colloquium speaker is Professor Luigi Luggiato. I think that most of you know him, so I will only say a few words of introduction. So Professor Luggiato has made major contributions in theoretical nonlinear and quantum optics, and he is especially known for the Luggiato-Lefebvre equation, which I think was proposed in 1987. He has made important and profound contributions to the field with a great impact, and that impact has been recognized by many awards. So I will not give here the full list of these awards. Let me only mention a few of them. So there is the Albert Michelson Medal in 1987, the Quantum Optics and Electronics Prize of the European Physical Society in 2003, the Max Born Award of the Optical Society of America in 2007, the Fermi Prize and Medal of the Italian Physical Society in 2008, and the list goes on. So I think that since we are all eager to hear the colloquium, we have been without colloquium for such a long time that we should start without further introduction. So Professor Luggiato, please take the floor. Thank you again also for accepting to give this colloquium in these difficult conditions, remote, but I think that will be appreciated by all of us. So thank you very much. Please start.
Okay, good afternoon, ladies and gentlemen. Of course, I would have much preferred to deliver this Solvay colloquium personally at Free University of Brussels for several obvious reasons, but especially because this would have given me the opportunity of meeting the dear friends that I have in this university. But okay, this is life, and therefore let me deliver you this remote colloquium. My talk is focused on the equation that I formulated more than 30 years ago in 1987, together with René Lefebvre, and in the following I will call this equation LLE. The program for my talk is that I will describe how this model was derived in order to provide a paradigm for optical pattern formation. Then we will see the connection with optical bistability. We will see we will discuss the matter of Turing patterns and the quantum aspects of this phenomena. We will discuss the matter of Kerr cavity solitons in the spatial domain. Then I will turn to the temporal longitudinal version of the LLE and to temporal longitudinal Kerr cavity solitons in fiber cavities. At this stage, I will address the key topic of broadband Kerr frequency comps and Kerr cavity solitons in microresonators with ultra high quality. Then we will see the connection between the LLE and Kerr frequency comps and Kerr cavity solitons. The last topic that I will consider is the frequency comps quantum cascade lasers, and then I will pass to the conclusions. The story starts in 1977, because in that year I spent a few months in the Free University of Brussels in the Chemie Physique department. I came there to collaborate with Paul Mandel. And just at that time, there was a publication of an important book by Nicolis and Prigogine, titled Self-Organization in Non-Equilibrium Systems, from Dissipative Structures to Order Through Fluctuations. So I studied this book, and I was especially impressed by the paradigmatic model for nonlinear chemical reactions that was formulated in 1968 by Prigogine and Lefebvre, a model that is usually called the Brussellator. This model consists in two coupled nonlinear equations for the normalized concentration of two reactants, X and Y. T bar, X bar, and Y bar are normalized space and time coordinates. A and B are parameters. D1 and D2 are the diffusion coefficients of the two reactants, and they multiply the transverse Laplacian. This model is a typical example of what is called a large aspect ratio system. This means that the system is very thin in the direction z, so that the z coordinate can be neglected, and the only two relevant spatial variables are the transverse variables x and y. And now the onset of a Turing instability gives rise to the appearance of beautiful spatial patterns. But now let us go to the case of optics. In this case, we have a laser beam that interacts with a nonlinear medium, and under appropriate conditions, the interaction gives rise to the appearance of spatial patterns in the section of the beam. In the bottom, you see some beautiful example of these transverse optical patterns. In the case of optics, the role of diffusion is played by diffraction. If we indicate by script E the electric field that I treat here as a scalar, we can express the field in terms of a carrier exponential that you see here, and of a slowly varying envelope function E. And it turns out that in the paraxial approximation, diffraction is described by the transverse Laplacian of the field envelope E. And this time the transverse Laplacian is multiplied by the imaginary unit. On the other hand, there is also a very important difference between the case of optics and the case of nonlinear chemical reactions. And we can realize this difference if we come back to the previous transparency. Because as we have seen, the laser beam propagates in the z direction, and therefore in the case of optics, the z coordinate cannot in general be neglected. However, in 1978, in collaboration with Bonifacio, I showed that under appropriate conditions, it is possible to neglect the z coordinate. This condition can be called high quality limit, or in the literature they are also called mean field limit or uniform field limit. But let us see how this high quality limit is defined. This limit is defined by two conditions. The first condition says that the nonlinear medium is contained in an optical cavity. Here, I consider the case of a ring cavity with two mirrors that are completely reflecting and two mirrors that are almost completely reflecting, in the sense that the transmissivity coefficient of these mirrors is very small. And this smallness of the transmissivity ensures the high quality of the cavity. The second condition states that in a single passage through the nonlinear medium, the field envelope undergoes a small variation. And this is because either the medium is very thin or because the nonlinearity is weak. Now let us put together the two conditions. Because of the small mirror transmissivity, the electric field goes through the nonlinear medium several times before getting out of the cavity. And therefore, the field envelope undergoes a sizable variation in time nonetheless. Now, the next topic to be discussed is the choice of the nonlinearity. As I told you, our aim was to construct a model with the same level of simplicity as the Brasseletto. And this implied that the model must involve only the field envelope, because the field envelope is a complex quantity, and therefore, in this way, the LLE amounts to a set of two real equations, exactly as the Brasseletto. In other words, the model must not include equations for the material variables. Now, in the choice of the nonlinearity, I followed a strict criterion of simplicity. In principle, the simplest nonlinearity is quadratic nonlinearity, but this is not appropriate for our purpose because quadratic nonlinearities involve two fields, two frequencies, the fundamental frequency and the second harmonic. And therefore, it involves two field envelopes. And instead, we want only one field envelope. Therefore, the simple choice is that of a cubic nonlinearity. This linearity consists in the field envelope multiplied by the modulus squared of the field envelope itself. And this is multiplied by the so-called chi3 coefficient, and is multiplied by the imaginary unit. This is called in the literature Kerr nonlinearity. So at this point, we are in condition to formulate the LLE. We have, first of all, the cubic nonlinearity, the Kerr term. Then we have the diffraction term with the transverse Laplacian. Then we have three terms that arise from the presence of the cavity. The first term is the input field that we assume to be stationary, uniform, and monochromatic. The second term is a damping term because the photons escape from the cavity. Therefore, there is a loss, and the field damping rate that I indicate by kappa is given by the velocity of light times the transmissivity coefficient of the mirrors divided by the cavity length. The last term is the cavity detuning term, where the cavity detuning parameter alpha is defined as the difference between the frequency omega naught, the input field, and the nearest cavity frequency divided by the field damping term kappa. Here, T bar, X bar, Y bar are again normalized space and time coordinates. Time is normalized to the inverse of the field damping rate kappa, while the two transverse coordinates X and Y are normalized to the diffraction length, which is defined as the ratio of the product of the wavelength times the cavity length divided by the transmissivity coefficient of the mirrors. In this equation, the F and D are normalized quantities, normalized in such a way that the number of independent parameters of the model is reduced to a minimum. And in fact, in this model, there are only two independent parameters that are the normalized input field F and the cavity detuning parameter alpha. At this point, there is an interesting observation that in this way, the LLE has the same level of simplicity as the Brasseletto, as we wanted, but it has even an advantage because the LLE is a realistic model. Whereas in order to describe nonlinear chemical reactions, it is necessary to use many more than two equations. as it is discussed in this book by Nicolis. But now let us focus on the LLE and let us consider its homogeneous stationary solutions. So we consider stationary solutions, so we set the derivative of the field envelope with respect to time equals 0. We consider homogeneous solution, so that we set the derivatives of the field envelope with respect to the spatial variables equal to 0. In this way, the LLE becomes the algebraic equation that you see here. Now it is convenient to reformulate this equation in terms of intensities instead of fields. And therefore, intensities corresponds to modulus squared of the field. And therefore, we take the modulus squared of this equation, and we obtain the equation that you see in the bottom. And then it turned out that this equation was already well known in the community of optical bistability, because it was formulated for the first time in 1976 by Gibbs, McConnell, and Venkatesan in their paper in which they reported on the first experimental observation of optical bistability. So let us see the connection with optical bistability. Let us consider the stationary LLE that we have just seen a moment ago. Let us fix the value of the normalized input field F, and let us plot the normalized intercavity intensity E as a function of the cavity detuning parameter alpha. Now it turns out that under appropriate conditions, this curve has a range of values of the cavity detuning parameter where there are 3 distinct stationary solutions. The intermediate solution is unstable, and therefore we have a bistable configuration with a hysteresis cycle. At this point, I analyzed the stability of these 2 stationary solutions and found that under appropriate conditions, there is a spatial modulation and instability that can give rise to the appearance of a spatial pattern. At this stage, I contacted René Lefebvre and asked him to calculate analytically the pattern that arises from this modulation instability. And his calculations showed that under appropriate conditions, the pattern was stable. So let us analyze, first of all, the case of Turing patterns. The Kerr nonlinearity corresponds to the physical process that is called 4-wave mixing. We have seen before that the input field propagates in the z direction. Now there is a 4-wave mixing process in which the system absorbs 2 photons from the input field and simultaneously emits 2 photons in symmetrically tilted directions, that is with values k and minus k of the transverse momentum. So if we consider the plane of the transverse momentum, this configuration corresponds to 3 points. The central point corresponds to the input field. The 2 symmetrical points correspond to the 2 symmetrically emitted tilted waves. At this point, there is a very important remark, and the remark is that the 2 photons that are emitted in transverse, in the 2 symmetrically tilted directions, are in a state of quantum entanglement. They are entangled in energy, they are entangled in momentum. And this fact is fundamental for the quantum aspects of optical patterns and for the field that is usually called quantum imaging. But now let us leave this field of quantum imaging. Let us come back simply to the classical picture. This 3-point configuration in the transverse plane corresponds to the emission of a field envelope, which is the sum of a constant term that arises from the input field plus two terms that arise from the two symmetrically emitted waves, and this provides a cosine contribution. So the emission arising from the Turing instability correspond to what is called a stripe pattern, or this is also often called roll pattern. However, it turns out that this roll pattern is unstable because there are further four-way mixing processes that destabilize it. So we have seen before that we start from a configuration with 3 points, point 0, point 1, and point 4. But now there is a further four-way mixing process in which the system absorbs one photon from beam 0, one photon from beam 1, and simultaneously emits two photons from in beams 2 and 6. And this happens with perfect conservation of energy and momentum. There is another also four-way mixing process in which the system absorbs one photon from beam 0, one photon from beam 4, and simultaneously emits two photons in beam 3 and 5. Therefore, the system assumes an hexagonal configuration, and in the bottom you see some examples of the hexagonal pattern that is emitted in this case. On the other hand, the Turing instability can give rise also to another kind of structure, which is called, and therefore, let us discuss this structure. Let us discuss about this matter that is called Kerr cavity solitons in the spatial domain. The hexagonal structure corresponds to a pattern which is formed by a regular array of intensity peaks that are ordered, are correlated to one another in such a way that they form the hexagonal pattern. There is also another structure that the Turing instability can produce, and this is called localized structure or cavity soliton. Here you see the example in which the system emits two cavity solitons. Localized structures in optics have been predicted by Mustafa-Tlidi, Mandel, and Lefebvre in this paper. And also the LLE predicts the possibility of cavity solitons, which therefore are called Kerr cavity solitons. And here you see the example of one Kerr cavity soliton, which is a single intensity peak surrounded by a number of diffraction rings. The possibility of this Kerr cavity solitons from the LLE was first shown theoretically by Tilly, Lefebvre, Willy Firth, and his collaborators. But now, after seeing, so we have seen the two kinds of patterns that the LLE can produce in the spatial domain, let us go to the topic of the temporal longitudinal version of the LLE and to temporal longitudinal Kerr cavity solitons in fiber cavities. Here we go to the work of Mark Helderman, Trillo, and Wabnitz. These authors consider the ring cavity, which was formed by a fiber with a Kerr nonlinearity. There was also, of course, an input field and an output field. And in order to describe this dissipative system, they were inspired by the analogy between two kinds of Hamiltonian solitons. Let us see these two kinds of Hamiltonian solitons. The first kind is temporal solitons that are peaks that travel in the longitudinal direction z without suffering distortion, and their behavior is governed by the temporal nonlinear Schrödinger equation, in which the spreading action of dispersion is counteracted by the cubic nonlinearity. On the other hand, spatial solitons are tubes of radiation that propagate without suffering diffraction, and their behavior is described by the spatial nonlinear Schrödinger equation, in which, with respect to the previous temporal equation, the dispersion term is replaced by the diffraction term that is described by the transverse Laplacian. So, Halterbach, Trillo, and Wabnitz were, in describing their fiber cavity, they were inspired by the analogy between these two kinds of Hamiltonian solitons. And they operated this analogy just in the opposite order of what I have showed you in the case of Hamiltonian solitons, because they arrived at an equation that is identical to the LLE that I have shown before, except for the fact that the diffraction term is replaced by a dispersion, by the dispersion term, which is just the second order derivative with respect to the longitudinal variable. And therefore, we see that the temporal longitudinal LLE is completely equivalent to the original LLE in the space, provided the original LLE is restricted to one transverse dimension. So it is a one-dimensional version of the LLE. Here, T bar and Z bar are again normalized space and time coordinates. T bar is defined as before. Z bar is a normalized longitudinal coordinate which incorporates the dispersion parameter. So I can draw here just a ring cavity, literally a ring with a z coordinate, an input field and an output field. An important remark is that once this equation has been solved, that is, once the Slowly-Vang envelope has been expressed in terms of time and space, the longitudinal coordinate z must be replaced by z minus time times vg, where vg is the group velocity. This means that the spatial pattern that originates from the Turing instability travels in the cavity with a velocity equal to the group velocity. Now there are two remarks. The first remark is that a model equivalent to the temporal longitudinal version of the LLE was introduced by Halterbach, Trillo, and Wabnitz, was derived from the Maxwell-Bloch equations in this paper in collaboration with my group. The second remark is that the pattern-forming instability of the temporal longitudinal LLE is a special case of the so-called multi-mode instability of optical bistability that was predicted together with Bonifacio in 1978. But now let us stick to the temporal longitudinal LLE. You have seen that the input field is uniform. However, the Turing instability gives rise to a special pattern. And this pattern can be, for example, a Turing pattern that circulates in the cavity and gives rise to a sequence of pulses in the output. Another possibility is that the Turing instability gives rise to a single cavity, single Kerr cavity soliton that circulates in the cavity and gives rise to a sequence of Kerr cavity solitons in the output. Now let us stick to this case of temporal longitudinal Kerr cavity solitons. Temporal cavity solitons are just narrow radiation peaks that circulate in the cavity without suffering distortion, and they circulate with a period which is equal to the cavity round trip time. And this temporal cavity solitons have been first observed in a silica optical fiber cavity by François Léo, Stéphane Cohen, and Helterman and collaborators. And so this concludes the topic of temporal longitudinal LLE. And now we can let me address the topic of broadband Kerr frequency combs and Kerr cavity solitons in microresonators of high quality. And up to now, we have described everything in time and space. If we go from time to frequency, we have that in the spectral domain, the periodic train of pulses that arises for the Turing instability corresponds to a comb of frequency. Now there is this important experiment performed by Tobias Kippenberg, Pascal Delay, and collaborators that first detected these Kerr frequency combs. And it turns out that these Kerr frequency combs can be really broadband because they can cover a frequency range which can arrive at the size of an octave. This and the following three transparencies are taken from a talk of Tobias Kippenberg. Here, the basic point is that the high quality limit that I defined before, theoretically, in these microresonators become reality, because these microresonators have a quality factor which can be larger than 10 to the 8 and even much larger. So these authors injected into the microresonator a field which has a single frequency, and in the output they found a combo of frequencies. They analyzed very carefully the frequency spacing between adjacent teeth of the frequency comb, and they confirmed that the frequency spacing is absolutely constant over all the frequency comb. They also varied the cavity detuning parameter, and in doing that, they found different kinds of patterns. They found first regular Turing patterns. Further, they found chaotic Turing patterns. And further on, they found, for example, this case of 4 Kerr cavity solitons, or in this case, a single Kerr cavity soliton, and the profile of the Kerr frequency comb, in this case, is extremely well approximated by a set-square configuration. So let us see the connection between the LLE and Kerr frequency combs and Kerr cavity solitons. A very important point is that Kerr frequency combs have been discovered without being aware of the LLE. However, shortly after, it became clear that the LLE not only describes very carefully Kerr frequency combs, but it is really the model that governs the features of Kerr frequency combs. This fact was pointed out by several authors as Matzko and collaborators, Chambo, Kippenberg, Herr and collaborators, Cohen and collaborators. Now I would like to show you this transparency by Jan Chembo. Here he compares the frequency comps detected in a microresonator, in a Kerr microresonator, with the corresponding simulations obtained using the LLE. And as you can see, the LLE is capable of reproducing very precisely very fine details of the frequency comps, with an agreement which covers a frequency range on the order of 80 dBs, and this corresponds to more than 300 frequency modes. Now, these microresonators are also quite miniaturized. They are quite small, and therefore they lend themselves naturally for applications. And applications have been already obtained in several fields as coherent as telecommunications, spectroscopy, atomic clocks, laser ranging, astrophysical parameter calibration. And here I have indicated two reviews of the applications of Kerr frequency comps. In the bottom, I have just indicated that recently the LLE has been generalized to the case of a Fabry-Perot cavity instead of a ring cavity in this paper. Now let me address the topic of frequency comps in quantum cascade lasers. Quantum cascade lasers have been realized by Federico Capasso and collaborators in 1994, and they have immediately attracted a lot of attention, especially because of the frequency range in which they operate. Now I show you this recent article by Capasso, Marco Piccardo and collaborators. This has appeared recently in Nature. It is entitled "The Frequency Comps Induced by Phase Turbulence." And in this paper, Piccardo, Capasso, and collaborators derive a complex Ginzburg-Landau equation for their ring quantum cascade laser near threshold. This is the complex Ginzburg-Landau equation. And now it turns out that this equation has exactly the same form of an equation that I formulated in 1988 together with Oldano and Narducci. I formulated this equation as the laser counterpart of the LLE that was formulated originally for a passive system without population inversion, whereas this is for an active system, a laser. The second of the derivative term here describes diffraction restricted to one transverse dimension, exactly as the original LLE. And therefore, one sees that this equation plays, with respect to quantum cascade lasers, the same role as the original LLE has played for for example, for microresonators. Therefore, we see from this that the LLE is capable of describing not only systems without any population inversion, but also quantum cascade lasers near threshold. And now I would like to indicate you this paper, which is going to appear in Physical Review Letters, in collaboration with Columbo, Piccardo, Prati, Capasso, and others. This is entitled Unified. This paper gives a unified picture and is entitled Unifying Frequency Comps in Active and Passive Cavities. So now we can pass to the conclusions. We have seen that there is an intrinsic connection between the LLE and Kerr frequency combs, Kerr cavity solitors. The fact that the Kerr frequency combs have been discovered without being aware of the LLE shows that sometimes science shows an evolution that is not linear, but is complex. Science is really a collective process. It's interesting also to remark that the criterion of simplicity by which I derived the LLE turned out to be visionary because it was visionary with respect to, for example, of Kerr frequency combs in Kerr microresonators. Finally, we have seen that the Kerr frequency combs can describe not only passive systems without population inversion, but also quantum cascade lasers near threshold. So at this point, I conclude my talk, and I thank you very much for your attention.
Thank you very much for this beautiful talk. Thank you also for keeping the time, which means that actually we have time for questions. So if you have a question, well, either you speak or maybe you raise your hand. There is you can use a Zoom raising hand function in reactions, I think. Yeah, you can raise a hand. So who starts?
Where does one find the hand to?
Well, we can hear you. So if you have a question, just go ahead. I mean, that would be easier.
So, of course, I'm quite fascinated by your talk, Luigi, because certainly in 1967, when we met and when we formulated that model, we had no idea of all the richness and the that would be discovered in this model. And there are many questions, of course, which can be asked about what you have said. But I will perhaps start with very general questions about the following. When one looks at the generalized case of the Fabry-Perot cavity, there is the situation that for given values of the constraints, you can have quite a lot of different structured states, which are stable at the same time. And you mentioned in your paper that some of those Turing patterns arise most frequently from vacuum fluctuations. Now, would it be possible that you explain a little more what you mean by that, and let's say how one should understand that? Because vacuum fluctuations are not in the model. And it is not clear to me why or how one could include such fluctuations into the model so that one can account for the choice between different possible patterns. Perhaps you remember that in 1987, we had a paper together with John Turner about fluctuations. And we tried to introduce fluctuations in the model. Well, we introduced, in fact, fluctuations in the model by we had only two parameters. And let's say we let fluctuate the detuning parameter. And so my question is, in a way, are such fluctuations, vacuum fluctuations, is it possible, if one wants to incorporate them in the model, to follow a line like we used there, which is, let's say, to assume that the fluctuations are described by some kind of stochastic differential equation or partial differential equation of the type. do you think, what is your opinion, or why do you say that vacuum fluctuations are involved? Are there internal fluctuations or external fluctuations, or are they coupled to the, or can one couple them to the model?
So, I mean, there is nothing mysterious about these vacuum fluctuations. The point is that you can find the patterns even without, let's say, fluctuations. But if you use equations without introducing fluctuations, of course, you must start from the stationary state, which is unstable, but to make manifest the instability, you must just shift the initial state from the stationary state by a little amount, and then therefore this shift gives rise to the pattern. If you introduce fluctuations, you have not, it is not necessary to introduce a shift, which is just a artificial procedure. And vacuum fluctuations can be introduced essentially by transforming the model into a set of stochastic equations, just adding some terms in the equations, in the, let's say, in the equation of the model that describe the, the fluctuations that simply arise from vacuum, in the sense that in nature there are always fluctuations, because vacuum is not nothing, but it's something that manifests itself just via fluctuations. And so one can describe these fluctuations by adding some stochastic terms in the equations of the model, and therefore they become Langevin equations.
Okay, thank you. I can see another question from Abdelmajid Taki, so please go ahead.
Majid Taki from Lille.
Hello.
Hi, hi Gigi. It was really very nice and very nice talk from you. I have one question that is a very old question that we addressed a long time ago. This concerns the two models, one from Picardo and the similarity with the Lejat-Lefebvre equation. It's one of your transparencies. In Lejat-Lefebvre equation, we see clearly that there is diffraction, and the diffraction is compensated by the nonlinearity, as we know, and this gives the first level to get a soliton. In the other equation you showed, there is the diffusion. And nonlinearity, it's not clear how diffusion is compensated with the nonlinearity. And my question is, would you like to comment about this? Because I know that you worked a lot about, and there was a lot of discussion before, and it's maybe very interesting to give us your opinion about these two facts that are completely different phenomena in physics, diffusion and diffraction.
Yeah. Well, I believe that I mean, diffusion plays a role in nonlinear chemical reactions, which is a very different context. And in that case, also the nonlinearity is very different. In the model by Prigogine and Lefebvre, there is a nonlinear, there are nonlinear terms that have nothing to do with the cubic nonlinearity. It's just different nonlinear terms. So I'm not sure that I have understood your question. I believe that in the case of optics, then you have the cubic nonlinearity that, as you said, compensates the effect of diffraction. And but in nonlinear chemical reactions, the nonlinearity is different. You have diffusion, but the nonlinearity is different.
But the equation is showed from the work of Picardo. Just the nonlinearity is cubic nonlinearity.
Ah, yes, yes. I know in the case of, but this is again a case of optics.
But he has also diffusion in addition to the diffraction in Loggiato-Lefebvre. This is
No, that's right. There is also a small diffusion term, which is non-negligible, is important. So there is this difference, but also in the optical model, if one goes to the case of quantum cascade laser, this I have not mentioned, but also in this case, one can obtain a diffusion term. And this is shown in the paper that I showed just at the end, before the conclusions. I indicated the paper in press in physical review letters. And in this paper, there is a derivation of an equation for the optical case of the quantum cascade laser, which contains the diffusion contribution. But you are right. I had not understood that you referred to that, the diffusion.
Yeah. Thank you, Gigi.
Thank you. I see that René has another question. So René, please go ahead. Well, at least René has raised his hand. We cannot hear you. You are still muted.
Yes, okay. I would like to make a small comment about the role of diffusion and dissipative structures and Turing structures. Most of the time, of course, when one studies Turing patterns, one assumes, in most papers, one assumes that the diffusion is linear. But this is not necessarily the case, of course, in chemistry. For example, diffusion can very often be a nonlinear phenomenon. And instead of a nonlinearity which is chemical, one can have a nonlinearity which is chemical plus a nonlinearity which is in the diffusion term. What happens then is that there is a phase transition which takes place. So in general, when one speaks of these Turing patterns, one does not speak of patterns which are related to nonlinearities in the diffusion. But as far as what one calls mathematically a Turing instability, well, this is essentially possible. It is possible to have a Turing instability and Turing patterns that are due to the nonlinearity of the diffusion. So that type of situation shows that, in fact, the Turing patterns are more general because the instability is related to a mathematical concept which is very different from the situation which is in general considered, depending on whether one takes into account phase transitions or not. So that's, I think it is important to realize that Turing patterns is not necessarily a non-equilibrium pattern.
I see. I see, very interesting.
Well, thank you also.
Thank you. Any other question or comment? Mustafa, please go ahead.
Okay, thank you, Marc. Thank you very much, Luigi, for the outstanding presentation. And it was very clear and limpid. So I would like, just as a comment, because recently we studied together with Shyam Gopalakrishnan the combined influence of dispersion and diffraction. And the formulation of this problem leads to a generalization of LLE equation in three-dimensional settings. where either Laplacian in 3D or in X, Y, and Z, or D'Alembert operator, depending whether the cavity operates in normal dispersion, anomalous dispersion regime. And so it was like, there is a theorem saying that the Schrödinger nonlinear equation, for instance, cannot admit more than one-dimensional solution because the solution collapse in the course of propagation. Where in the cavity, we succeed to stabilize this light bullet. So it is a 3D confinement of light that propagate without distortion, without, they keep the same radius with the same width in course of propagation, although there is dispersion and diffraction, and there is no collapse, despite there is nonlinearity. So we characterize this, and we succeed to have not only one or two, but clusters of them that moves out of the cavity with the group velocity of the light. And in addition, in high intensity regime, where the dynamics becomes more complex, then we show that there is extreme event to so-called rogue waves in three-dimensional model. So this paper now is accepted in PRL. It will be published very soon. This is just for information. Thank you very much, Mark.
Thank you very much for this interesting information.
Other question? Any other question? I think René is still his hand raised, but it's probably from the previous
well, I
question.
could ask another question, but there are many questions possible, of course.
Okay,
well, maybe,
so maybe the last one.
Okay. Finally, I would like to say something perhaps more about the question at the beginning about the fluctuations. Let's say, make it somewhat more precise what I had in mind about that. In fact, in the procedure to get the equation, one eliminates the atomic variables. One supposes that the relaxation time of the atomic variables is very fast, much faster than the relaxation time of the field in the cavity. Now, that is of course sufficient to obtain deterministic evolution equation that we have obtained. But if one thinks of the fluctuations, then one must also, if one wants to model them and to incorporate them into the description, know something about the correlation time of the fluctuations in space and the correlation of those fluctuations in space and in time in order to model them. Because depending on whether the fluctuations are faster or slower than the atomic variables which have been eliminated, one can have very different behaviors. And in fact, under some circumstances, if the ratio, for example, between the relaxation time of the fluctuations itself and the relaxation time of the atomic variables, if there are for some values of this ratio, one can have bifurcations and transitions in the model which are due to the fluctuations and completely due to the fluctuations, and which have nothing to do with averaging out fluctuations, because there is no longer averaging out of fluctuations. And so I think it would be very interesting to have more information about the correlation time and the distribution in space of, if it is possible, of frequency of vacuum fluctuations. So is it possible to make more precise the statistics of the vacuum fluctuations in order to know how to incorporate them in the model? What do you think, Luigi?
I am inclined to describe the vacuum fluctuations as fluctuations which are zero correlation time, white in time and also in space. So they are delta correlated in time and delta correlated in space. I am inclined to describe them in this way.
Okay, thank you. I understand that, and I was expecting that answer to you, of you. But you know that if one looks at for conditions where fluctuations have an influence on the macroscopic description, then it is necessary that the relaxation time of the fluctuations of the atomic variables be faster or slower than the relaxation time of the vacuum fluctuation. So it would matter, really, and make a difference in the bifurcation diagrams if one can change away from this simplification, let's say, to assume that vacuum fluctuations are Gaussian white noise. But okay, I've never seen somebody who has done that, and I don't know if it is, I'm not a physicist, so I'm not really know if it is something which may be undertaken meaningfully or not.
I'm not aware, of any paper that I studied for this problem, but I agree that this is an interesting problem to be addressed.
Okay, well, maybe we shall be able to discuss that another time.
It's a non-trivial problem.
I think so. Thank you, and maybe we discuss more about that another time.
Yes.
Okay, thank you. So with this last question, let's thank our speaker again for this very interesting talk, and also for having accepted to give it online. So thank you very much, and good evening.
Thank you very much, Dr. Barney. Thank you for your words.
And good